Good morning, everyone. Today we're going to look at our last section of this unit, section 5.5. It's called optimization. So our goal is to use optimization to find the best solution. What this really is the extreme value theorem in context. Quick review of the extreme value theorem: if you have a function that's closed, continuous, and differentiable, then there must exist a maximum and a minimum within the given interval. So what we're going to do is we're going to take a look at the fact that we know that that theorem is true. So we're going to optimize by finding the best solution, aka find the maximum or the minimum value. So what are some things that we would want to maximize or minimize? These are not limited to these items, but here's just a couple ideas. We could want to maximize the area, maximize the amount of money you take, your profit, the revenue, your volume even. Things to minimize: perimeter, debt, cost, surface area, right? Now keep in mind you could also look to maximize surface area, or you might want to minimize volume, so these aren't set to their categories. Alright, let's take a look at a quick example here. You don't have to write this one down at all, it's just to get your mind thinking. Here's the scenario. In an apartment complex, an apartment complex has 250 apartments to rent. If they rent X number of apartments and their monthly profit, given by dollars, is the function P of X. So here's the function for the monthly profit. How many apartments should they rent in order to maximize their profit? Well, what does logic tell you? What's your initial guess? If you own this company, what would you want to do, right? Kind of have an idea. You're probably thinking, I'm going to rent all 250 apartments. That should maximize the amount of money I get. Well, let's use calculus to justify why. First thing we're going to look at is just something that's not written down, but it's implied. Our domain within this context is we can rent 0 apartments, or we could rent 250 apartments, or any whole number in between. Right? So that's just an implied domain. So what are we going to do? We have to find the maximum. Well, in order to find a maximum, we need to figure out when the derivative is equal to 0. We have to find the critical points. So you can see I took the derivative here. I'm going to set it equal to 0. And then I'm just going to use algebra to solve. All right, so I get a critical point at x equals 200. Now, is 200 going to maximize my profit, or would one of the endpoints? That's where we have to go ahead and check our initial conditions, the critical points. So I'm going to check 0. If I rented 0 apartments, I would be negative $80,000 as a monthly profit. I'd be in the hole $80,000 every month. You don't want to do that. If I rented 200 apartments, I would have a positive profit of $240,000. And then if I rented 250, you can see that I would actually be less than, I'd only be making $220,000 a month. So maybe this answer isn't what you thought, but the owner should rent out 200 apartments to maximize their profit. So really quick background, why might they not want to rent out all 250? Well, you can think of different costs that are associated with owning an apartment complex, right? You have maintenance, you have upkeep, painting. Anything goes wrong, you're probably responsible for it. You know, like an air conditioner, a heater, a furnace, water heater, anything like that. So there's actually more to a situation like this. But it's kind of interesting how 200 isn't really probably what your initial guess was. So our goal is to basically look at this idea of optimization. So here are some basic steps that we did, and I'll kind of walk you through what we did with that last example. We didn't really need to draw a picture, but that's always the first thing I recommend, is draw a picture. And then we're going to use a variable and associate the expressions needed for the measurements. So notice we said a variable. That's the goal, is we want to write everything written in one variable when possible. I'll show you that. And then you need to write your equation with your variable. We usually call it f of x. That's what we want to optimize. To optimize, we have to find the derivative of that equation, set it equal to 0, or figure out when it does not exist. We're going to look for domain and endpoints as well, like we saw in the last example, and then check your actual answer. So I'm going to shrink this really quick. If you would like, you could put this all on one page for your notes. Just go ahead and write it down as soon as I get this up here. Excuse me. Go ahead and hit pause. So I kind of group, you'll see, I kind of do the first 3 steps all in one. I look at the picture, figure out what equations and variables I need, and then I write my single function. And then I think of 4 and 5 and 6 all kind of going together. Take the function, find the derivative, check the critical values and the endpoints. And then 7 is the most important. Make sure you answer the actual question. A lot of times that's often overlooked. All right, so let's take a look at a couple examples here. This would be the problem just like this. It's create the open box with the largest possible volume from a piece of 28 centimeters by 21.5 centimeter cardboard by cutting out the corners and folding up the sides. So how do we actually find the largest possible volume for an example like this? Well, let's set up a picture first. What do they give us? You have to excuse kind of trying to save time here, so I have a lot of things preloaded. But let's start right here. You have a piece of cardboard. You're going to cut a square out of each corner, so then when you fold up that square, you can actually fold along these lines right here. And you can see that if I fold up each flap, it'll turn into this 3-dimensional model. Right, so what do we know? We know that this length is 28, 21.5, and we're cutting the height out of each one. So I know on my 3-dimensional model, when I fold this up, this flap right here is going to be the height of the volume. But what about the length and the width? Well, how long is this side right here? Well, this side is the length from here to here. Now, it's not 28, it's 28, but we took away an h on this side and an h on this side. So this length from here to here is 28 minus the 2 h's that we took off. And if we take that same logic and apply it to the width, the 21.5, we're taking away a length of h here and h here. So we're taking away a 2h from the 21.5. So here's my equation for volume. That's what I want to maximize. Right? So I'm going to write the equation with respect to h. Notice how each variable here is h. I didn't use length times width times height. I used the substituted variables with h in them. So now I have all the variables written in terms of h. I'm going to FOIL and expand this whole thing out and combine my like terms. That I'm going to just assume you're going to press pause. You'll do that on your own. Once it's all multiplied out, I get a new expression, condensed, all the like terms are added together, and I have this volume formula, right? So now our goal, find the largest possible volume. Well, in order to do that, we need calculus. We have to take the derivative of each piece with respect to h, and then we're going to set it equal to 0. All right. Now, this is a tricky spot. You could try to factor this, but it's not going to factor. In fact, it's going to look something like this. If you were to graph this, you'll get 2 zeros that you need to find. So I'm going to make the assumption that you know how to find those zeros in your calculator. I found them right here. I got 2 zeros, one at 4.019 and the other at 12.480. Now let's think about both of these answers. This is almost 12.5 inches. If I cut 12.5 inches across to get this x and another 12.5 inches, that's going to go 12.5 inches down here, and then I'm going to cut 12.5 inches here. Well, 12.5 and 12.5 is 25. It's going to completely cut off this side. So in that case, this answer right here is too large. We can't use it. We have to use the 4.0196533. So that's the h value that I'm going to use. And then the question said, find the largest possible volume. So I have my expression for width, length, and height. I'm going to find those values. So I took h and I plugged it back into each one of these. And I have my length, being 19.606. Notice how I took all the decimals? I did that because I don't really want to round until the end of my answer. The very final answer is when I round. Otherwise, keep everything exactly the way it is. So then here's the width. I plugged in this answer for h up here, times it by 2, 21.5 minus that answer. And then the height is excuse me, the height is exactly h. Then you can multiply all that together, and there is your maximum volume. All right, so quick recap. What did we do? We drew a picture. We actually created that picture, so now I have all the expressions written in terms of one variable h. Took the volume equation, did some algebra, so I could take the derivative, found the critical value that applied to the actual context of this problem, the answer that worked, and then I used that answer by rereading the question to find the largest possible volume, plugged it in, and found the volume. Excuse me. Let's take a look at another one. So this is what your situation would look like. A rancher wants to fence in a rectangular area for his cattle to graze. He will use a river as one side of the rectangle in order to increase the area he can enclose. Well, because he's using the river, we're making the assumption that the cattle will never cross into the river, so that's protecting it. So he really only needs to fence 3 sides of the rectangle. If the rancher has 12,000 feet of fencing, what is the largest rectangular area that can be enclosed? So we actually know 2 things now. We know our perimeter, which is 12,000 feet, and we want to maximize the area. So I'm thinking we actually have 2 things going on. Our goal is to maximize area. So I'm going to write that equation. The area of a rectangle is length times width, right? That's what I'm going to end up taking the derivative of, because that's what I want to find. But I need to write this equation all in the same variable. So let's go to our picture. Here's our picture. We've got a rectangular piece. X times x, or excuse me, x and x are the sides, and length y is how long the length is. So what do I know? Well, I know area is length times width, right? X times y. But I've got a problem here. Not both of these items are written in terms of the same variable. So we're going to go back to this perimeter idea, our constraints, and we're going to say we know something else here. Let me cover this up. So what do we know? We know that the perimeter is both x's plus a y. Right? Now, if the water wasn't here, it would be x plus y plus y, but the water is replacing our fencing need on that side. All right? So what we can do is we know the perimeter is equal to 12,000. I need to rewrite this so it's in terms of one of the variables. I get to choose, and since y is really easy to solve for, let's just move the 2x over to this side. So now I know exactly what y is equal to. I'm going to go ahead and instead of doing the area as x times y, I'm going to replace x. I'm going to replace y with what y is equal to, so x is the only variable in the equation. And then we're going to use algebra, simplify, distribute, excuse me. Take the derivative of both pieces, solve for x, and notice you get x being 3,000 feet. So the algebra is hopefully pretty friendly and quick. You guys can solve that. Now we're not done because the question said, what is the largest rectangular area? So I then have to use the fact that I know what x is. We're going to plug it right back in here for y, for x to find y. So if I plug in x is 3,000 times by 2, subtract 12,000, I get y equaling 6,000 feet. So I know x, I know y. I can find the maximum area very quickly. 3,000 times 6,000 tells me that I will have 18 million square feet or square foot as the largest possible rectangular area that I can include. Now I will say, because this problem is pretty famous, every once in a while they say, well, what if a farmer wants to divide up this land and we put another X right here? Right? So what if I put another fence right here? All that would do, it wouldn't change any of the work that we did over here, but it would change our perimeter. Our perimeter would be X plus X plus X now, so I'd have 3X plus 1y, and that would just change the equation that we're plugging in. Yes, it'll change the numbers, but the work is basically all the same. So just be aware that every once in a while they can do that. They can say, you've got an extra side length of fence being put in here that's parallel to the other sides. Okay, let's take a look at this one. A rectangular storage container with an open top is to have a volume of 50 cubic feet. Notice, we know the volume. So right away, that's what my constraint is. I'm limited to having 50 cubic feet of volume. So keep that in mind. The length of the base of the container is to be twice the width. The material for the sides costs $5 per square foot, and the material for the base costs $8 per square foot. Find the dimensions that minimize the cost of material. So this one's kind of tricky. I want to minimize the cost of material. Now, when we say cost of material, that's basically, you're kind of thinking your area of each side or your surface area. So let's take a look. First thing we'll do is draw a picture. And what do we know? We know that the length of the base is twice its width. So I don't know what the width is. I can call it x, which makes the length 2 times that. Now we don't know anything about the height and how it relates to the x. So unfortunately, I can't write that in terms of x. I have to use h. But what we do know is we know that the constraint will give us a chance to write this h in terms of x. We know that we are limited to 50 cubic feet due to volume. So I know that the length, the width, times the height has to equal 50. If I multiply that together, I end up with 2x squared equals h. If I divide by 2x squared, I get h is equal to 50 over 2x squared, or divide by 2, 50 divided by x squared. So now I have an expression written in terms of x. So the equation that I want to minimize is the cost. Well, let's think about how we would set up the cost equation. What is cost? Cost is the area of the base times by $8 per square foot plus the area of the front side, but I'm going to times that by 2 because I have a front and a back, and that is $5 per square foot plus the 2 sides. Right, and the sides are still $5 per square foot. I have 2 of them, but notice that the front and the sides are different dimensions, so that's why I had to write them separately. And also notice it's a open top, so I do not have 2 bases, I only have 1. So then we have to set up the costs, and I have to find the area of the base. Well, that's 2x times x, or 2x squared. So $8 times 2x squared. And then the area of the front, now the front is kind of tricky. We're going to take the fact that we know what h is equal to. So I'm going to do 2x times 25x. And if you wanted to write that out quick, 2x times 25x squared. Notice the x squared is going to go away. And I'm left with 2 times 25 over x, or 50x. That would be the area of the front side, right? And then notice 2 times 5 gave me the 10. And then now I have to find the area of this side, which is x times 25 over x. So that's just going to cross out an x on the bottom. And it'll leave me with 25x for the area of one of those sides, but I have 2 of them. So I'll do 2 times 5 is 10, and then the area of this side. So I'm going to combine those together. Oops. So I end up with my new expression, 10 times 50 is 500. Instead of writing divide by x, remember we could write that as x to the negative 1. Same thing here, 10 times 25 divided by x is the same as 250 x to the negative 1 power. Well, these are like terms, so I can add those together. And now I'm at the point where I can actually take the derivative, because that's our whole goal. Right? Our whole goal is to write the equation in one variable, in this case x, Do some algebra to simplify it, and then take the derivative. And now we're going to set the derivative equal to 0. And notice what I did. Instead of writing, when I took the derivative, instead of writing x to the negative second power, I'm going to take that and put it underneath the negative 750. And then, because it's negative, I'm going to add it over to the other side here. Right? And what does that do? That sets up a proportion. Now I can cross multiply, because this is 32x over 1. We can always put the 1 down there. Cross multiply, go ahead and solve, divide by 32, take the cube roots, and I get 2.862. You should probably take this to a few more decimals just to be more accurate. But notice that's the x value that we need. And now all we have to do is answer the question. Find the dimensions. So they didn't say minimize the cost, but find the dimensions. So I have to just find the dimensions, height, length, and width, by taking what we just found x to be and plugging it in for x. Right, so 2.862 gave me a length of 5.724 feet. The width is going to stay whatever our x was, and then the height is 25 divided by x squared, which ends up being 3.052 feet. So from this, I could then find the minimum cost, but they just wanted the dimensions. All right, last one. Hopefully you're getting the hang of this. This one's a little tricky as well. Rico takes his dog Fido out to play fetch by the park by a lake. Fido likes to run and swim. In fact, Fido can run at a rate of 4 feet per second and can swim at a rate of 3 feet per second. If Rico throws the ball 50 feet down the shoreline and 25 feet into the water, how far should Fido run and swim in order to reach the ball as fast as possible? So we're looking to maximize our... Actually, I take that back. We're looking to minimize, because we want to do this as fast as possible, but we want to maximize the speed, or the time that it takes to get there. So look at this position. Now, it says Rico throws the ball 50 feet down the shoreline and 25 feet into the water. Clearly, Rico's going to throw it at a diagonal. He's not going to throw it this way and this way, but that helps us set up this problem of having a right triangle. Now, I set up a little bit here. We know the length is 50 feet. We know that we're 25 feet into the water. 25 feet into the water. What Fido wants to do is Fido wants to run a little bit and then swim to the ball. So we don't know the distance. We're going to make this algebraically nicer, I'm going to call the distance between where Fido jumps into the water and the perpendicular, we're going to call that x. And that leaves, you'll see why I called that x in a second. That leaves the fact that Fido would run 50 minus x feet. That's how far he would run until he jumped into the water. The next thing we need is we need the length that Fido is going to actually swim. Well, notice, if this is x and this is 25, we can use Pythagorean theorem and find the variable for the hypotenuse, the expression. So we could have called this x and this 50 minus x, but that makes this algebra a little nastier when doing Pythagorean theorem. So it's friendlier to call this distance x. And then we can say, okay, to find the length of the hypotenuse, c squared equals x squared plus 25. Do some quick algebra, get c by itself, and now I have the exact length that I need for the distance that Fido would swim. All right, so here's my equation. I have the distance that he would run, the distance he would swim. The only difference is we have to actually now apply the rate. So just taking the running and the swimming with the length, we have to actually figure out the length, the rate. So what do we know? We know that distance equals rate times time, right? That's our dirt formula from physics. What if I just want to get the time in there, right? So what if I divide the over by the rate? So if I took the distance divided by the rate, that will give me the time that it takes for running and the time for swimming. Well, the rate that Fido is going to be running is 4 feet per second. So I'm just going to divide by 4, and then the swimming is 3 feet per second. So notice, what I'll do is I'll take the running length, and I'm going to multiply that by 1/4, because that's basically dividing by the rate of 4 feet per second. And I'm going to take the swimming equation, the length that Fido would swim, and we're going to times that by 1/3, or really just dividing it by 3. So here's my equation that I want to minimize. I want to find the derivative of. What I would do first is do some algebra to clean this up. Distribute, distribute, and then here we can't really distribute, but I'm going to rewrite this square root as the power of 1/2. What that does is that allows us to easier take the derivative of. So take the derivative of each piece, nothing super crazy here. Then we've got the chain rule, so 1/2 comes down, multiplies by the 1/6. Keep the inside, take 1 away from the top, and don't forget about your chain rule. The derivative of the inside is 2x. Excuse me. So now I have to set the derivative equal to 0. I'm going to rewrite this part here just so it's friendlier. 1/6 times 2 is 1/3, and the x is going to stay up top. And then this whole piece right here is going to be rewritten in the denominator as the square root of x squared plus 625. Notice this negative 1/4. If I move it over to the other side, that gives me a proportion, and I can cross multiply proportions. Right? So I'm just going to kind of assume you guys are pretty good at that, and just take a look at this work. You can pause the video and follow through. Cross multiply, divide by 3. I'm going to square all the pieces, so I get 16x squared over 9. And now it's a proportion again, so I'm going to cross multiply, distribute the 9, do algebra. All your algebra will get you to 28.347. And then we're going to plug it back in for x. Right? And that will tell me the distance that Fido ran. Actually, that's all they're looking for, is the distance that he ran. So we're just going to do 28.34 minus 50. And that'll be the distance that Fido ran. And the distance that he swam, plug 28.347 into x here. Square it, add 625, square root, and here's the distance that Fido would run and swim, and that would be the fastest possible route to take to get to the ball. All right, like I said, you can hit pause at any point. Go back and rewatch these videos. Tonight's homework is in the textbook. I gave you a little hint on number 2. You need the volume of the cylinder and the surface area of the cylinder. One of those is your constraints, and the other one is what you want to minimize or maximize. I can't remember. All right, good luck.